Auzubillahiminash-shaytanir-rajeem. Bismillahir-rahmanir-rahim. Assalamu alaikum, dear student. In the last lecture, we discussed the various postulates of valence and electron pair repulsion theory. In today's lecture, we will discuss that how this theory is applied to explain the geometry of various molecules. So in last class, we discussed the various postulate of valential electron pair repulsion theory. In today's lecture, we will discuss the shape of various molecule depending on the valence electron, the bonded pair of electron and the lone pair of electron will explain the shape of molecule. And at the end, we will discuss the limitation of valential electron pair repulsion theory. So how the valential electron pair repulsion theory explain the geometry of a molecule. In valence shell electron pair repulsion theory, the least electronegative atom must be selected as the central atom, except hydrogen. For example, we can see over here the example of carbon dioxide molecule. Carbon is less electronegative or least electronegative as compared to oxygen. Therefore, carbon is at the metal, and the other electronegative atoms are present linked to the central atom, carbon, which is least electronegative. Here we can see the boron trifluoride molecule, and in boron trifluoride molecule, boron is less electronegative as compared to fluorine. So, according to the valence shell electron pair repulsion theory, the least electronegative atom must be present at the center, while the other atoms must be linked to the central atom. Similarly, we can see the example of phosphorus pentachloride. Phosphorus is less electronegative, so it is in the center, and chlorine is more electronegative, and it is in around the the phosphorus atom. But in case of hydrogen, if there are hydrogen atom, hydrogen is less electronegative, but generally hydrogen is not present at the center. For example, we can see over here the water molecule, hydrogen is exceptional case, while in all other cases, the least electronegative atom will be considered as the central atom. But when there is a hydrogen atom, in this case, hydrogen will not be the central atom, as we can see in the water molecule that the oxygen is more electronegative, but it is the central atom, and hydrogen is linked to the oxygen atom. Similarly, we can see the example of ammonia. So hydrogen is exceptional, therefore hydrogen is outer atom, while the nitrogen is more electronegative, but it is the central atom. So this is the first rule to predict the shape of a molecule by valence shell electron pair repulsion theory is that the least electronegative atom must be selected as the central atom, but the hydrogen is an exceptional case. Here we can see the methane molecule. The carbon is more electronegative as compared to hydrogen atom, but as the hydrogen is exceptional, therefore it will be present outside the central atom. Now, how we can predict the shape of molecule by valence shell electron pair repulsion theory? We can see here different types of molecule with various geometry, and the valence shell electron pair numbers of the central atom define the geometry of the molecule. For example, if there is two bonded pair of electrons, then the structure will be linear and it will be at maximum distance and at angle will be 180. If there is three bonded pair of electrons, then the structure will be trigonal planar. And in all these molecules, only the bonded pair of electron is shown. If there are four bonded pair of electron, then the structure will be tetrahedral. If there is five bonded pair of electron, then the structure will be trigonal bipyramidal. If there is six pair of bonded electrons, then the structure will be octahedral. And if there are seven bonded pair of electrons, then the structure will be pentagonal bipyramidal. So these bonded pair of valence electron decide the shape of molecule. If it is two bonded pair of electrons, the structure will be linear. Here we can see the example of two bonded pair of electron. For example, carbon dioxide have the linear structure because it have two bonded pair of electron, beryllium chloride and beryllium hydride. If there is three bonded pair of electron, then the structure will be trigonal planar. Example is boron trifluoride and sulfur trioxide. If the bonded pair of electron is 4, then the structure will be tetrahedral, and example is the sulfate ion and the methane molecule. If there is 5 bonded pair of electron, then the structure will be trigonal bipyramidal, and example is phosphorus pentachloride. If there is 6 bonded pair of electron, then the structure will be octahedral. We can see the structure of octahedral. And the example is sulfur hexafluoride. And if there is 7 bonded pair of electron, then the structure will be pentagonal bipyramidal. For example, iodine heptafluoride. So the structure of molecule or geometry of molecule depend upon the numbers of valence bonded electron. So on the basis of valence bonded electron, we can decide the geometry of a given molecule. So in this slide, we can see only the bonded pair of electron, that if there is 2 bonded pair of electron, the structure will be linear. If 3, structure will be trigonal pyramidal. If 7, the structure will be pentagonal bipyramidal. Here we can see that if there is a bonded pair of electron, 2 bonded pair of electron, the structure will be linear, as one can see in the first row of this table. If there is 3 bonded valence electron, and if the 3 bonded pair of electron is bonded one, then the structure will be trigonal planar. But if there is 2 bonded pair of electron and 1 lone pair of electron, then the structure will be angular R band, as we can see in this table in the second column and the second row. If there is 4 bonded pair of electron, then the structure will be tetrahedral. But if there is 3 bonded pair of electron and 1 lone pair of electron, then the structure will be trigonal pyramidal. The reason for the distorted order are not regular structure is that the bonded pair of electron and the lone pair of electron have a more repulsion as compared to the bonded pair of electron. Therefore, this structure have a pyramidal, trigonal pyramidal structure. If there is 2 bonded pair of electron and 2 lone pair of electron, then the structure is also bent or angular. If there is 5 bonded pair of electron and then 5 bond is pair of bonded electron, then the structure will be trigonal bipyramidal. But if there is 4 bonded pair of electron and 1 lone pair of electron, then we can see the structure as a seesaw sawhorse structure. And if there is 3 bonded pair of electron and 2 lone pair of electron, then it is T-shaped. And if it have 2 bonded pair of electron and 3 lone pair of electron, then the structure will be linear. So on the basis of valence shell electron pair which are present, which is bonded pair of electron and lone pair of electron, decide the shape of molecule on the basis of valence shell electron pair repulsion theory. They arrange themselves in such a way that the repulsion is minimized, and when the repulsion is minimized when they are at maximum distance. The shape of molecule with only 2 atoms is always linear because the bonded electrons are at maximum distance when they are at linear shape, because in this case the repulsion is minimized. So therefore when there is 2 atoms, then always the structure is linear. If the central atom is linked to similar atom and is surrounded by a bond pair of electron only, the repulsion between them are similar. As a result, the shape of the molecule is symmetrical and the molecule is said to have regular geometry, as we can see in the structure of methane molecule. If the central atom is linked to different atoms are surrounded by bond pair as well as lone pair of electron, the repulsion between them is different. As a result, the shape of the molecule has an irregular or distorted geometry, as we see in the last slide in table, that if there is bonded pair of electron and lone pair of electron, then the structure is T-shaped or bend shape or an irregular shape because the repulsion is different between the bonded pair of electron and the lone pair of electron. The exact shape of the molecule depends upon the total numbers of electrons present around the central atom. We discussed the valence shell electron pair repulsion theory, and we discussed that how the valence shell electron pair repulsion theory describe the geometry of various molecules. But here are some limitation of the valence shell electron pair repulsion theory. The first limitation is this, that this theory failed to explain the isoelectronic species, those species which have the same numbers of electron, but generally they have different shape. So the species may vary in shape despite having the same numbers of electrons. So the valence shell electron pair repulsion theory do not explain the geometry of the isoelectronic species. The second limitation is that it predicts that halides of group 2 elements will have a linear structure where their actual structure is a bent one. We can see over here the magnesium chloride molecule, and according to valence shell electron pair repulsion theory, if it have linear structure, it will have minimum repulsion. But generally, when it is observed that the magnesium chloride have this type of structure, so the valence shell electron pair repulsion theory doesn't explain the halides of group 2 element that they have, why they have bent structure. The valence shell electron repulsion theorem does not shed any light on the compounds of transition metal, because we discussed most of the other molecules, but it doesn't tell anything about the transition metal. So it's also a limitation of the valence shell electron repulsion theory. The structure of several such compound transition metal cannot be correctly described by this theory. This is because the valence shell electron pair repulsion theory does not take into account the associated size of the subsequent groups and the lone pair that are inactive. So in today's lecture, we discussed that how the valence shell electron pair repulsion theory is applied to describe the structure of molecule, and we um, see that the structure of molecule or geometry of molecule depended upon the numbers of valence electron, that how many bonded pair of electron and how many lone pair of electron are present. So on the basis of numbers of bonded electron and non-pair of electron, we can explain the geometry of various molecule by applying the valence shell electron pair repulsion theory. Thank you.